Hey everyone, today we bring a new edition of Datons Stories, where we build stories with data by coding in Python. Today we're going to look at the energy mix without nuclear energy, which according to the PNIEC plans, which is a government plan to shut down nuclear power plants, we need to see what other technologies will replace them and how we can forecast things like CO2 emissions, market prices, whether it'll make things cheaper or more expensive. You can do a lot of cool stuff with simulation. But beyond that, the optimization problem is what's really interesting. Because based on installed capacity, meaning if we have 7 nuclear reactors, what's usually the price? At what hours? If we have 6, what will it be? Because each nuclear reactor typically gives us around 1000 modules of energy. To give you an idea, at any given hour, demand usually reaches between 30,000 modules and 40,000, around 42,000 modules to supply all of Spain. And if Spain has 7 nuclear reactors producing energy, that means nuclear covers roughly 20% of all the energy generated in Spain. If nuclear goes away, well, another technology will have to replace it. But of course, we often have renewable energies that are intermittent, because when the sun is out but there are clouds, that energy can't be fully generated. If there's a lot of wind, sometimes wind energy can't be produced either, and then we have to rely on other generation sources like natural gas and so on. So it will be really interesting to use historical data to run this simulation and see what happens under different scenarios. But the most important thing will be based on a certain installed capacity, how much energy do I project will be generated in the future. Because this is also how companies that develop energy solutions for industrial clients can offer them a feasibility analysis of a new installation in a more accurate way, having those future estimates based on installed capacity. Because if you also look at solar energy now, it's brought prices way down during daytime hours because there's plenty of sun, and solar energy, I think by law, can't be priced above €0 per MWh because it's renewable. So what ends up happening is if I produce at most 20,000 twice of solar, then how much gas will be generated and so on. So as gas, which does actually cost money, gets used more, gets priced higher at the end of a market clearing curve where they buy energy, that's the price that ultimately gets set. But what happens, since there are so many solar panels, the spread, let's say, gets stretched and the price doesn't clear at high levels, meaning at high euro values on the market clearing curve. And that's why we sometimes see negative prices during certain hours of the day. But, well, beyond the analytical stuff, let's get into today's stream. Just a reminder, today we'll be working with machine learning to make those generation estimates. And on the other hand, we'll use optimization that, based on the estimated numbers, will simulate what will happen 20 to 30 years from now, in 2035, which is when the nuclear plants are scheduled to be decommissioned. So remember that all of this comes from Datons.com, the platform we have here, where I'm collecting all the live streams I've been doing. Here you can see all of them. both the ones I do in English and in Spanish. It's me live coding solutions with Python using data, whether it's infrastructure or applications, which is more the vibe coding side. And since today we're working with a data story about what happens without nuclear energy, we have it right here in Datons Stories. You can see we have many other energy related topics. For example, here's battery optimization. You can check it out. And here you have the recording, just like you're watching today. Coding here, step by step, no tricks. On the other hand, we also offer from Datons programming solutions applied to data, whether it's building infrastructure like servers with applications that automate processes, integrating other servers, APIs, intelligent systems powered by artificial intelligence, web applications, and SaaS platforms. This is also something we're currently developing with clients. If you're interested, we can have a discovery call to see what's up, if we can collaborate or just get to know each other. What I can offer or what you're working on, no problem, just click here. Here you can see what we'll cover during the call. You can see other clients who've already trusted us. And here you can see my availability to schedule a call and catch up on how we can collaborate. All right, let's go back to Datons Stories. The context of the PNIEC and the nuclear shutdown is that right now in Spain, we have 7 reactors generating 7,400 megawatt-hours of total capacity. Keeping in mind that during daytime hours, demand usually reaches around 30,000 to 40,000 MWh. We can see this here on ESIOS, where all the grid operator information is available. Here we can see, for example, generation and consumption. If we click on the indicator, what's the demand? During daytime hours, when there's a lot of, everyone's active, producing, industry, people at home, turning on heating and all that, here we see demand reaching 35,000 nuls in dollar. If we consider that nuclear energy provides us with 7,000, well, that's 20% of the total. You can find much more indicator data here on ESIOS, which shows real-time data. Here at night, when it's colder, people have their heating on, so there's a bit more electricity demand. You can also see on this page how much of that electricity each technology is generating. You can see that here under measured generation. We click on Analyze indicator, and here we can see how the energy mix is composed. The thing is, it's not working here right now. You can also click here on generation and consumption. And here, let's see if under the electricity balance generation, we should be able to see, here it is. Here we can see right now how the mix is composed. If you look at, for example, this is for today, what's been scheduled in P48, because all this was done yesterday. The companies that generate electricity with solar plants, wind farms, they say, well, I'll sell you this many MW at this price, 100 euros per MWs, or 200 euros, or 1 euro per MWs, and that's how generation works. So when we have the scheduled energy, here we can see from the previous day what the quantities are. For example, Stife. If we go to nuclear energy, we can see here that we have 1,434 MNIs. Give me a second, I'm getting a phone call. Okay, sorry about that, I'm back. So what I was saying, we have right now a scheduled nuclear generation of 1,434. That means that out of the 7 nuclear reactors, probably only 1 is running, or maybe 1.5. Here we have the rest of the generation by technology. So as you can see, there's a lot of information from the grid operator that can be used to run those future simulations right here. So we then have that let's say, the decommissioning of the nuclear reactors is scheduled in a staggered way, with Almaraz scheduled to be decommissioned in 2027 and progressively until 2035, when all of them will be decommissioned. At least that's the plan. Then we need to keep in mind that if nuclear generation is 20% of total generation, we also need to take into account the capacity factor. This means that if I could use this technology during all possible hours, which in the case of nuclear would be 365 days a year, the capacity factor is 89%, meaning almost 90% of the time I'll be able to harness that energy. This isn't the case with something like wind energy, because it's not always windy, or solar, where it's impossible to have sun during the night, so it can't generate. However, it still counts as installed capacity in the system. Anyway, all these things are what we'll take into account for the future simulation to see what the maximum generation is across the year or across several years based on the capacity factor for a specific hour. Then we simulate into the future with all energy sources. So the problem we have here is precisely that installed capacity is not the same as hour by hour generation. Nuclear runs 24/7, solar only when there's sun. That's why the capacity factor is usually around 20%. That is for every megawatt it generates per year. Meaning for every MW of installation, it generates about 500 watts per year. With wind, it's a bit more because it can run during the day and at night, so it's almost 25%. And ultimately, we need 5 times more solar MW to replace 1 MW of nuclear energy. That's the estimate. But of course, if enough solar energy is also installed, then that replacement could work out, but that's where the debate is. In our case, we're going to stick mostly to showing the numbers, trying not to lean one way or the other. Let's go with the capacity factors for each one, which are the ones you see. We already discussed this, so we won't go over it again. And the model we're going to apply is machine learning on one hand to make the estimates and optimization with real constraints. Because, for example, if I have 7 reactors that give me at most 7,400 megawatt-hour, it can't be that with 6 reactors I get 8,000 MWh. So these kinds of limitations when running the simulation are what we need to account for in the optimization model. So we're going to use historical data from the website I showed you earlier from ESIOS. On the other hand, we'll use a machine learning model, probably a decision tree, to make the future estimates. Optimization to adjust the physical limits with the capacity factor, and the simulation 30 years into the future to also know, for example, what the mix will look like, how many emissions, what the cost will be. Here we'll capture patterns, seasonal trends, respecting the laws of physics, the real data from ESIOS, and the feasibility of new installations. So the scenarios that could cover that nuclear energy are renewables only, meaning solar, wind, but with the downside that we'll have intermittency. Now, scenario B, which is what happened in Germany. I don't know if it's because they didn't install enough. I haven't looked deep into it. But if you look at the news, in Germany, you'll see they decommissioned all their nuclear plants, and now they have to inject gas and even coal, which is much more polluting, to meet demand. And that generates way more CO2 emissions, which contradicts the energy transition plans. And in scenario C, we'd have an optimized mix where we have renewables with gas, but limited gas, because we'd rely more on battery storage and interconnection between countries. So we'd have minimum cost, but of course this is the nice to have, the ideal. But maybe that's not feasible, and maybe we'd be fooling ourselves, because nuclear can already supply well with cheap prices and no pollution, since nuclear plants don't emit CO2. And we could just, without getting into more trouble, be trying to solve problems that might not exist. But since the whole idea is about wanting more renewable energy from solar, from wind, not relying so much on radioactive materials in this case, although nuclear plants do handle them very safely and with strict protocols. Actually, from people I follow on social media, you can see that workers at nuclear plants often get told, well, I'd like to see you living next to a nuclear plant. And actually the workers do live near the nuclear plants because it's their workplace and nothing happens to them. So let's get to the data. We'll be using Python as our tool for coding, libraries like Pandas for working with data tables, Plotly for visualization, and the RE API as our data source. So let's get to it. Facts, not opinions. If you see me going off on tangents here, call me out, do me that favor, and I'll focus more on the data. All right, let's go then. By the way, feel free to leave a comment, whether you're watching right now or you'll watch it later and you loved it, because especially these sessions, I want them to be quite interactive. Let's open Visual Studio. And I'm going to start with a project that I already had more or less built around this kind of setup. I'll explain it now. First, let me check that everything's looking good with the stream. Okay, perfect. So let's get to it. I was saying that I had a project already started on how to do this optimization. We had here the data based on what the energy generation is with the P48 schedule, which is the one that currently stands as scheduled after all the energy markets. Then over here, we do a future estimate of the P48 of that generation. The estimate also based on the PNIEC, which is the government's plan to redistribute the installation of capacity by technology, remove the nuclear plants and replace them with solar and wind. And here we have machine learning models to estimate the hourly ratio, also the capacity, which are several that we use in the system. Then over here I have other data. The important thing here is the scripts. So in the scripts we have the data preparation. Let's take a look. Here we have, well, we import the Pandas library for working with tables. Here we already have the PNIEC information as of 2019. This was the wind installed capacity for that month in January. Then in February, it progresses, for example, here in 2030, which is what's known from the PNIEC. For the training data, we have here 62,000 of installed capacity. If we then look at nuclear energy, we have here 7,399 right now, as I mentioned before. And for 2030, we have 381, meaning they would have already decommissioned 4 nuclear plants. All the documentation and references, let me see if I have it here. References here. Here I have some documentation you can look up online. Here, for example, from Diego Rodriguez. We had an interesting table where he showed with the PNIEC focused mainly on CO2 emissions. Here we have the assumptions. There's a table here that I was quite interested in, which was this one. Look, here we have, for example, the PNIEC 2020. It had already planned to decommission several nuclear plants, and the actual data shows that none were decommissioned. Here we also have, for example, how in reality what ends up happening, because investors need to put money in so that these solar plant installations, you see, when you're on the train, for example, or the wind turbines actually get built. You need to invest money to make it happen. And sometimes the processes aren't that smooth, whether due to lack of investment, permits, environmental impact, and so on. So that's why often the targets aren't met. In fact, here we have in the 2020 PNIEC for wind, the goal was 50,000 Pottern Mount Dutcher, and it turns out we still have 30,000. So in the end, the PNIEC is great as a statement of intent in many cases. Someone I listen to, for example, is Javier Revuelta. In case you want to follow him. I think he worked at ERA, and now he works as senior principal at AFRAI, which is a consultancy for energy topics. And what he usually says about the PNIEC, if I understood correctly, is that it's great as a statement of intent. But in the end, when it materializes in reality, it turns out to be something else. Here, for example, he posts his opinions with concrete data. He has tons of experience in the sector. And here you can see, for example, how he talks about a more realistic and useful PNIEC for energy policy. All right, let's continue here with the numbers. Let's see. I don't think there was any table there that I needed. This one here, it talks about generation, the possible scenarios. Something like this is what we'll try to build today. I already have something done. So it'll be much more straightforward and we'll just need to fine tune. I'll show you how I've set it up in a moment. Then there are others here, other studies. This one here, it shows investment, transport, GDP. These are charts with lots of trends. Here, for example, it talks about atmospheric pollutants, more of a general overview. Then what we have here from government documentation, it's the draft for the PNIEC from June 2023. I don't know if they've updated it. Well, all the documentation about the plan and the numbers. There was a table around here about that statement of intent for the capacity to be installed. Let me see if I can find it here. General objectives, transport, dimension, let me look around here. Installed. Installed. Let me find the table here. Here it is. This is the one that tells us that statement of intent, official draft from the government that tells us, for example, what the intention would be for 2030. Let's see if this is the 2035 one. Let's see if this is the 2035 Buitven. No, I don't see it here. All right, we'll get into the details later. Let's look at the latest reports here. Economic impact. To make this go less technical, let's see. No, there was no reason why. Here it is. Here it is, because this is it. Evolution of the primary energy dependency ratio. Here it shows national production with gas, electricity. I'm looking for the table of assumptions up to 2035 for installed capacity, which was a table. There's still no table here. Okay. All right. Here it is. Here it is. So here, of course, it tells us the target. Here we have nuclear for 2030, that it should be $3 Flamengo, reducing and decommissioning further plants, that gas. Here we have combined cycle gas. Stays the same, and solar PV, it should even double from what we currently have, although this is 2025. It's a projection that was made. Here you have the image of the plan itself. All right, there might be other tables here. Here they talk about the trends and all that. Okay, so let's continue here. When preparing the data, for example, what you see is that information in this table, but having done an interpolation, because in this case, we need to know what the energy is for the intermediate years. And so the optimization can work even. It's not just doing it year by year, but also doing it month by month, which is what you'll see next. Here we do the preprocessing, and you can see how we're going from having the information year by year to having the information month by month with an interpolation. Although here, basically, what I'm doing is repeating the same installed capacity value for the entire year, all months of the year. Then here I export it as CSV, and this would be, let's say, the data that the model will use as explanatory variables, meaning based on this installed capacity, well, how much generation will there be? Then here I have another script for pre-processing. And of course, here I also took into account how to remove biomass and biogas. Here we start working with combined demand. This is where we were doing a mapping to keep everything consistent. The demand which you end up downloading from REO, the grid operator, what has been the real-time demand of what actually happened. Here you can see, for example, the demand FS base. Here we have it, demand. What I'm not sure about is in which part I downloaded the demand. Anyway, it's a file I have somewhere around here. That's it. If you, for example, want to download the data, like for instance the demand, the trick is, let's create a new folder here. Let's call it a new notebook, downloads. And to download the demand, we need to import the ESIOS library. For that, you need to install it with pip install Python ESIOS. Since I already have it installed, I don't need to. Even if you go to GitHub, here you'll see how to use this library. In the examples we have in the library, in the ESIOS API, a structure where first we get the entry points, which are the indicators, that is how much solar energy has been generated, how much wind energy has been generated. And on the other hand, we have the files, which are the famous I9s that tell you which nuclear plant or which solar plant has generated how much energy. This information is very valuable for those who do trading. We set up the API key, and in my case, it's just entering a code. If you're curious about it, ask me in the comments, and I'll tell you how to get it. Okay, I'm going to put it here on another screen. And once it's set up, you hit restart. We run it again, and now we have the client ready. So if I ask the client to go to the endpoint named indicators, why is that making noise? All right. the entry point for the indicators, how does it work? Well, first I need to, if I want to get a list of all the indicators, I can pass it here, and here we see all the codes. For example, a scheduled hydro generation, and we need to find out what the demand code is. Once we have the codes, we go to the entry point, select that indicator, which will be a number, and retrieve it. In our case, if we go to the ESIOS API website, it usually turns out that the demand indicator matches one of the numbers in the URL here. For example, 45545, which might be the real demand. If I click here, this is to view it in the chart. I can see it on its own, and the number it gives me here, they show it as analysis. I can't see it here. I think it's the number I mentioned earlier. Let's try it. If not, what we can also do more easily is export the data frame to Excel, and here we put indicators. And here we can search for the real demand. And it's 1153, which comes in MW8. Let's put it here. Let's say this is the indicator we're working with. And with that indicator, we're going to request the historical data. So we give it a start date, for example, let's give it 2015, and an end date. I don't think the system is set up for just the year. Let's try. Let's give it up to 2025. We run it. So here it's querying RES data to give us all the generation, all the demand, hour by hour, or every 15 minutes from 2015 to 2025. It usually takes a while. I just didn't save it here. I've got the data now. I'm going to stop it. I'll set a shorter range so we can see it quickly. 2024. And let's see. And of course, well, that's still quite a lot of data. Here we have it. It even includes the real demand broken down by each zone. Interesting. Wait, I got the number wrong. 1153. Oh no, I got confused. Be careful with the Excel, because since I searched for 1153, it's not actually the number. It's this one here, which is the column. What we were looking at before was measured nuclear generation, which of course here only the locations where we have nuclear power plants installed will show up. Okay, so let's change this indicator. One of the advantages of programming is that the code you already have, you simply change the value and it returns the same thing. Let's see. Okay. Thanks. All right, we've got it. If you look closely, it's even every 5 minutes. The whole year, if we select here and make the chart, we can see, for example, for a specific day, that curve we saw at the beginning, where at night, when there's barely any demand, up to daytime when everyone is active, working, and so on, and at night before going to sleep, people turn on the heating and such. Okay, so that's how we can download this data, and then to have it in a data file, what we do here is export it. So here you'll see, for example, that in the processed data, we have the demand here. Let me find it. Demands. Is that even possible? Here it is. It's in data app. Here you have it. So then this demand data point, this could be the demand forecast. If I want to see the forecast demands, I have it here in this file. Now look at what I did in this project. I'm going to collapse this for now. And then here in this project, where I have everything in scripts, the modeling part, once I downloaded all the data, one of them was the demand. So to estimate the demand, look at what I did here at the beginning of the notebook. I imported preprocessing, which is a library I have here in utils. And this is the one that here, for example, preprocessing. I use it later to prepare the time features of the explanatory variable. Because of course, here, what information can I reuse for the demand? Well, for example, whether it's a weekend or not. And also not to play too much with the hours of the day, because the hours go 0, at 1, at 2, at 3, up to 24. But at 24, it goes back to 0, 0 again. So all that continuity can't be captured by numbers going from 0 to 23 or from 1 to 24. It is captured when you apply the cosine transformation, and that's the reason I created the sinusoidal hour and the cosinusoidal hour. Same thing for the week, right? The days of the week, day 1, day 2, day 3, up to 7. Then the next one is 1 again, but there's continuity. Although in this case, you can differentiate more by each day. That's why I even added a new column specifically for weekends. After doing this pre-processing, we move on to the modeling, which is what variable do I want to predict? Well, I want to predict the real demand. So I set the real demand as the target variable y and the rest. That's why I remove the real demand, which is in the target variable. The rest I set as explanatory variables. Then here I do a split between training data and test data, because this is like taking an exam. If you're preparing for an exam, for example, you have 100 historical questions and you study all 100 of them. And then at home, before the exam, without looking at the questions, but you've already studied the 100 questions, you take the exam again, and it turns out you got 90, right? So you think, wow, I nailed it, I got 90, I'm going to get a 9 out of 10. Then the actual exam comes and you got a 4. Why? Because you were overtrained on the historical questions, but the exam has new questions. So here with machine learning models, the same thing happens. If we don't do the separation ourselves, we think the demand prediction is going to be great, but then in reality, in day-to-day operation, it's not. We deviate too much from what's actually demanded in terms of energy. So, what's the other strategy to see if we can improve the model, or in the study analogy, can we keep studying more questions? Well, from the 100 historical questions, you study 80 and leave 20 unseen. And those 20 unseen ones, after studying, You answer them without knowing the answers and test how well your training prepared you for questions you didn't see while studying. In the case of machine learning models, it's the same. How to face new demand days that you haven't seen because they're in the future. So that's the system of splitting data into training and validation. Here, in this case, we use 20% for testing. If we build a model, which in this case is tree-based, XGB regressor, XGBoosting, if you don't know what that is, there's a really good YouTube channel called StatQuest for learning how machine learning models work. If I search here for XGBoosting, here you'll see how he explains it fantastically. You can see he explains it super well, with charts, what each part does. With very to the point examples, if you want to check it out to understand how these algorithms work internally. Although if you're just getting into machine learning and all that, what I recommend is that you look at the base model that XGBoosting is built on, which in this case is the decision tree. So you search decision tree, YouTube, and it'll come up. So that's the one you watch. And you'll understand how tree-based algorithms work. Good. We come back after building this model, we see how good it is, and it turns out it's 83, 0.83. But of course, what does that mean? Well, when we do the score with data that are numerical values, not percentages. Let me check this here. I'm going to ask our friend ChatGPT about this. Let's see, first, let's go here. If I use this model in Python and do the score, what do I get? A percentage or another metric? Right. It's r squared, which is a number between 0 and 1, and it's not very intuitive to interpret. So we should use the MIE here, which is the mean absolute error, or the root mean squared error. So let's do that, which will give us a more meaningful number. I don't even remember how I had this set up. Let's see if it works. Here we need to run everything from the beginning. So we come here. We run the previous parts. Although there's already an error here, let's deal with these kinds of errors. This is because in this environment I have here, I don't have the library installed. So I'm going to come here and let's type which UV. If I put the question mark, the exclamation mark is to see where I'm running. Although here it was Mamba install XGBoost, that's because I use a different tool. Normally, if you want to install it, you do pip install XGBoost. I use Mamba, which is like a Conda distribution, a Python package manager. Here, for example, it's already installed, so if I run it again, there shouldn't be any issues. And now we have the model computed. Here it tells me with what parameters. We calculate the score, we still get the same result. And here we're going to look at the MAE and the RMSE. We get 1880. What does this number mean? 1880 and two values. Notice something. In the real data, we have these numbers here. If I make a histogram, we see the whole distribution here. Let me see if I can do how to make density. The density, so you can see it like the Gaussian bell curve. We just need to add density true here. Let's put here density true, but it doesn't show up. And data equals, well, this is enough. Notice something. If this is the chart of the generation, I'm going to remove the density because the generation chart, and if you ask what's the probability that Spain's energy demand at any given time is between 15,000 megawatt-hour and 42,000 megawatt-hours, well, it'll be around 27,000, which is roughly the middle value, the mean, where mean, median, and mode coincides. In this case, yes, because the chart looks more like a Gaussian bell curve. So we can say the average demand in Spain is about 27,500 natlers megawatt-hours, but that exact value isn't fixed. It keeps changing. So from all the variation, which is the difference with each number, I would need to calculate what difference there is with the mean of the real data. Then on top of that, mean I calculate the sum, but if I calculate the sum, it'll be 0 because there are negative and positive numbers when taking each hour of generation and subtracting the mean. So how do we counteract that? We apply squaring first, and then here is where we apply the sum. But now we need to counteract that squaring. So how do we apply it? With the square root. And here when we apply the square roots to the sum, wait, hold on, let me get this right. First with the sum, notice that I shouldn't be doing the sum because I'm essentially calculating a kind of average among all the differences between the real data and the mean. So here, instead of the sum, we should use the mean and we get this value, but of course we need to counteract the squaring we did before, and that's when we get 4,578, which is basically the standard deviation. You'll see it here in the formula. If you search a standard deviation formula, you see here we have the estimated value, the actual data point x sub I, minus the estimated value, which is the mean. You square it, sum them up, and divide by n. Essentially, that's what's called the mean. You apply the square to counteract it, and you get this Gaussian bell curve, which is the most important one in statistics because it tells us that, let me see if it shows up here. Here it is. What does this Gaussian bell curve tell us? If the mean or the value you estimate, which in our case is the data from the mean of the data here, 27,900 megawatts was the value we had before, which falls in the middle. If I apply the standard deviation, which is this other number, the 4,578, let me make sure. 3, that's the standard deviation, exactly. 4,579, 78. what we do here is, if I take 28,000 and subtract the 4,000, I'm left with 24,000. So what's the probability that Spain's electricity demand is between 24,000 and 32,000, which is the mean plus the standard deviation? It's 68%, which is the sum of the density under the bell curve. So when we talk about values, where we have the machine learning model prediction, we need to look at the RMSE, and it says 1,680. What does that mean? That our model predicts with 68% precision within 1,180 manvia above or below any given prediction, which is pretty good, because if we consider what the total generation, the total demand is, the ratio turns out quite compact. Here we were doing, for example, with the mean, and we have here, for example, if we divide by 1, something like 93%, but don't trust this number too much, but basically think of it as the model being about 93% good. With this data, we know that the demand estimate is going to be quite good for running the full future simulation. We have the forecast, and here we have it up to the year 2030. So that forecast, that future demand prediction, is what we save in this data we have here. Then if we look at the forecast here, of course, what am I using? The hour ratio or the capacity ratio. How did I calculate that? Well, if we come here to the capacity factor, which is also commonly called, here I load all the ingredients, demand, the PNIEC, the PNIEC explanatory variables, a selection, installed capacity, and P48's generation. And what do we do here? We load everything into this dictionary and do the pre-processing to normalize by hours, because if you notice, we have to sometimes fill in the data because here I have missing values, and models, when you give them a missing value, everything breaks. You can't do sums or means with missing values. So here I fill them in with this resample and missing value interpolation. Then we limit the PNIEC data to the real installed capacity, and that information we take to the Parquet file for each of them. All right, that looks correct. And here's the interesting part, which is where we calculate the capacity factor, and I calculate the capacity factor within each year, week, and weekend. You give me the maximum value, which is everything that could be generated from there. I divide the real data, and that's how I'm working with the total that could be generated. However, another ratio we can use is based on installed capacity, but many times installed capacity doesn't make sense, because even though at night I have 20,000 MW of solar, I'm counting it because I'm thinking, hey, I could generate 20,000 first memduals with this solar energy. But due to physical constraints, you can't actually do that. That's why in this case, I prefer to apply the capacity factor based on the year, week, and month. For each hour, I get the maximum for that technology and do the calculation. Why am I not specifying the technology here? Because it already comes in the data frame as columns. If we run everything, here you'll see in the P48 base data frame that we have columns with the technologies. So I can then group by year, week, and weekend to find the maximum. Good, so I saved that information as an ingredient and name it with the file name, which here is our ratio or capacity ratio. Up here at the beginning of the notebook, I set a parameter for how I'm going to use the ratio based on the maximum capacity per hour or installed capacity. So here I use ratio max as false, which means we use capacity based. And what we have with capacity based is this. But of course, why do we use capacity based here? Because the data we're working with from the PNIEC is installed capacity. So I'll know what the PNIEC's installed capacity will be up to 2030, but I won't know what the maximum generation will be across all hours or weeks for that technology. So it's easier to work with the model based on installed capacity. And of course, here we start doing the fit to test some models. Here we do a grid search to find the best possible model with XGBoosting, considering various parameters. And here we get the predictions, which are quite good. We have a 75% here, and here we break them down by the error. Some are more accurate than others. For example, winds, combined cycle gas, and solar PV are the hardest ones for the model to predict. And here we can see that Gaussian bell curve for each one. And this is where I save the simulation. But of course, in these models, no optimization is applied. This was just the capacity factor making a future estimate with those models, and that's it. But what I'd really like is to make a future forecast for the next 30 years up to 2035, which is when the nuclear plants are scheduled to be decommissioned. So you more or less get what the ingredients are in this mix. We work with capacity factors, machine learning models, download data from ARIA, preprocess it, calculate how reliable these model estimates are, 90%, 80%, 70%. Because if you make an estimate with a model that gives you, I don't know, 50% reliability, then any simulation you run has no solid foundation. That's why you need to make sure the estimates are as accurate as possible. Then we move on to the forecast part, which is pretty much the same, normalizing by hours. Here, I worked with the PNIEC, did a reindexing to make it hour by hour. And here we start with the capacity factor simulation using all the PNIEC data. And with that model we computed earlier, I'm now going to make the energy prediction because I already have the installed capacity according to the PNIEC up to 2030. Remember that earlier when building the model, which we had here, the XGBoosting, when I use the model, I pass it X-train and XY. If I look at this data, when I prepare it, at most it goes up to 2023 because that's the real data I know, and that's what I can then compare to see how good the model is. Taking maybe up to 2021 to train, to study, and then I take the exam on 2022 and 2023. That's where we found the model is 75% reliable. And that exact model is what we then save in a pickle file containing the numbers of the mathematical equation. And we take it to make the future estimate, but not just up to 2023, but up to 2030, which is exactly the data we have from the PNIEC for installed capacity. And here, when we make the prediction, first we load that computed model and then make the prediction. So we compose the final data frame, and here it tells us the estimate not of the generation but of the capacity factor. Remember, we're working with the capacity factor, which is like the percentage of energy that could be generated. Here I adjust limits on the data because you can't generate more than one, meaning you can't generate more than the installed capacity or the maximum we calculated. So here we adjust the limits both above and below, and then we calculate the generation by simply multiplying the capacity factor by the installed capacity from the PNIEC. Let's run everything and see that future prediction, see how much sense it makes. So here it says wind at 11 p.m. generates about $9,000 Mandodalir, solar 691, which doesn't make sense because it's nighttime. Same here, in the morning it generates 18, that would need some fine-tuning, and nuclear, notice that at the beginning, year 2019, where there is nuclear 7,000 MMW, but in 2030, when only 3,000 remain, according to the PNIEC plan, we get 2,300. So the simulation is already giving quite reasonable and significant numbers hour by hour, because many times the studies you see out there, the reports, they don't do these estimates at a granular level hour by hour, which is where you gain precision in the models. Instead, they do it with the yearly aggregate. There they lose a lot of data that's key, because you're assuming with averages, yearly averages, monthly averages, if they do month by month. But here we go to the maximum granularity, which is hour by hour. So all those future forecasts, those estimates, have a higher degree of precision. This is super, super important. Good. All these predictions, we save them here in forecast P48. Then I was working on other models, making the annual summary of what could happen up to the year 2030. The reporting, you need to be very careful here. Then I made another model. I mean, it's a bit messy here. I remember I did this back in the day. ChatGPT didn't even exist yet. So now what I'm going to do is, based on all this project, we're going to ask the chatbot to package it up nicely for me. I put my key here. Let's open the Claude extension. Here it says restart. You need to have it installed. If not, search here for Claude Code. You also need the extension. Although, well, this time I'm going to work with the ChatGPT-1, which was Codex, so it won't fail on me. There it is. Got you right here. And now, let's activate it. We have Codex right here. It's showing here what it's going to do. Let's create a new conversation, and here we'll tell it, let's see what model we're using. They put extra height reasoning here, and here I want to use Codex 3, the new one they just released. You set it to local project, let permission full access continue anyway. we're going to say, hey, it's been a long time, I don't know when, since I worked on this project, and now I'm picking it back up. But of course, I need to restructure it into a new repository with Python files instead of notebook files. Basically, I want to systematize it. And one of the main ideas I have is that this system could take as inputs what the installed capacity will be year by year for each technology. I could even do it every 2 years, every 3 years, or I give it 2020, 2030, 2030, or 2100, and from there it can run the simulation. So I need the output to be that hour by hour forecast. Yes, hour by hour for now, and I think we also had a web application frontend to visualize these results. So I think what you're going to package for me is, on one hand, the code structured as a command line interface for all these calculations, and then the front-end part with a Streamlit for visualization. But first, I want you to tell me what the repository structure will be. A whole application here that transcribes everything for you. So we hit send and let's see what comes out, baby. Let's see what comes out. Okay, so let's see. What do we do now? Let's see the response here from the chat. What it proposed. Having this repository, configurations, technology, notebooks, legacy, nuclear energy, the Streamlit application, which looks perfect to me. I mean, this is pretty good. Yeah. Onward and upwards. Let's see what it does. Of course, this repository, I made it back in the day when there was no artificial intelligence yet. And you have to code everything from scratch. Let me see, it's cutting me off. Let's see. See, it's going to create all these folders. There's something I want to do first, which is initialize git make a commit, so we know how the repository looked before this refactoring. That way, if tomorrow the AI messes things up, I can go back to what I originally made. Usually that doesn't happen though. The truth is that artificial intelligence works pretty well for doing these kinds of migrations. All right. Let's see. Okay. What do you guys think so far? Have you worked on this before? Simulations or something similar, a future prediction? What do you think? About simulations or something like that? Simulations or something? Anything similar? It created this and it's asking me to normalize it. The thing is, I still see the plan here, or go ahead with everything. It can't even see me here anymore. Where's the camera? Can it still see me with the AI? Yeah. Should I move over here? Yeah. All right. Also, what I don't like right now about the folder is that it hasn't archived this properly. It's all mixed together here. It is good that this src folder is here though. I'm not sure if it made a git commit or not. I think it did. Before the refactoring, here it starts creating the files inside src. Okay, that's good. Looking good. Here I'm starting to do some housekeeping so I can keep track of things. Here I can't tell what it's done and what it hasn't. Here it did the review. Yeah, I can see it. Here, instead of doing this to remove other renewables, biomass or biogas, I'll reselect it because there were some technologies I didn't have data for. I think biogas was one of them. It continues here. Done. The before and after. The cool part is going to be that after all this refactoring, we'll see the web front-end application and we'll see how, if I change the installed capacity, the future forecast will look different. And we can also improve the optimization system because, of course, the optimization is also something I tried here. There are many ways to do it, right? I mean, it's not one brute force approach, which is the one I explained to you, modeling. We have this here. So here, what do we do with this? Well, because when I make the future prediction, and then here I apply the limits, this is essentially part of the optimization algorithm, because with the predictions that the machine learning model has made, we're adjusting them to match reality. We're setting constraints. The thing is, this can be done after making the predictions, which isn't really what you'd call optimization or linear programming. If we want to do it through linear programming, we'd have to do it within the algorithm itself when it generates the results. The problem is that's more computationally expensive and takes much longer. I think I had something here in the model, and here it is. This library called Spolt is the one that handles those optimizations. Here is where it defines the variables to be between 0 and 1 based on the capacity factor. Here you add a penalty so that if the conditions aren't met, it works one way or another. And then it solves the problem. The thing is, of course, I think for each technology, it took quite a while. There are several ways to compute all this optimization. And the important thing there is having a system that lets you try different approaches. Here it says maintaining tests. And that's exactly what I'm going to tell the chat now. Hey, when we do the optimizations, there are many ways to optimize. Beyond adapting the logic I have in the notebook, I'd like to have a configurable system to specify different conditions. At different times for the optimizations, what do you recommend here? And I can't, let me, oh wait, it knows here. Whisper, whisper. But sometimes it gets stuck on me. This is good practice, asking the chat before going all out with the code implementation, asking it what it would do. And here it tells me the optimizer should have 3 layers with a base model, constraint objectives, with components here, and with a YAML file. And here it says to validate the schema. Let's see how it does it. Something's coming through here. And this is going to be the PNIEC thing. I don't know if in the end they've modified it, made some new draft. No, it was here. Here it says 2021 to 2030. Then here it says 2023. This was September 24th. The update. Here it is. Right, this was the one. I think I already downloaded it, or not. Let's see if it comes up here, the installation. It's asking me here to, I'm going to open the other chat. Let's add government references here, this document. Let's reference it here. 2024. Let's ask which page has the installed capacity planning. It's 736 pages. Better let the chat read it. And here I read it. Here it is, with triple, meaning export to a raw text. Read, markdown, and tell me what I should search for to find it. Well, of course, the AI has to go through it page by page, and a lot of times what it does is read the image. Take a screenshot. We could be here all day. But here I get a graph and I want a table. This is on page 25. What I don't know here is if the PNIEC is made for 2030 and here in 2023, which in theory is the 2023 PNIEC talking about what will happen in 2030. I think page 75, here it comes. Here we can see what's intended with updated data. Here, honestly, I don't even know what I've told you, because in the end, I understand the numbers well for building the models for future estimates. I understand some of it. For example, they plan to have 76,000 megawatts of solar PV. We would see with those 76,000 megawatts how much energy would actually be generated in the mix. Because this doesn't mean that all 76,000 megawatts of solar PV will actually happen. You also have to see if demand is going to grow, which is also what's expected. There are many factors. I mean, if all of Spain were covered in solar panels for energy, well, at night we'd have blackouts because there's no sun at night. All right. Let's see how Codex is doing. I think Codex is still working on it here. We've got it maxed out. It says emissions here. I think it even added the CO2 emissions for each one, which, well, that's also interesting. Here gas shows 0.307 and solar 2, which apparently also generates a sum. I suppose that's from manufacturing the materials during installation, which usually take into account. The program is turning out pretty well. Let's see. Let's see if it finishes. I don't think it's broken or anything. What else needs to be done? Man, I'm so sleepy. On top of all this streaming, I'm also developing applications for companies. Life doesn't give you enough hours for everything. I've got some serious accumulated sleep debt, but hey, with excitement. From here, what I'll probably do is publish some applications so you can interact with these future forecasts, and you set the installed capacity, and based on those assumptions, you get the hour by hour generation estimated for as many years as you want. Next important thing, migrating your real notebook logic to the general package at minimum. I'm going to apply everything and you'll have to excuse me. I'm taking a break. And I'll be back later. All right, we're back. So this should be finished by now. Let's go ahead and run the application, live and direct. Let's run the application. I'm still... Okay, so it's available at this URL. Let's go to localhost, Streamlit. Now it should work. Well, if it's not my Qt already, thanks. Notice here that it gave me a command to run. If I open it, I copy it here. I take it to the terminal and run it. And now it should be here. Let's go. And here we have the simulator. So if I now here in the input, hopefully it did it right. It says it's loading, perfect. Now here I'm entering the capacity factor, but I wouldn't want to work with the capacity factor, but rather with the installed capacity. Let's tell it here. What if instead of working with the capacity factor as input, we use the installed capacity, which is ultimately what we'll know from the PNIEC. Here it says capacity factor, gas, hydro. Here we always run. Right, here. The capacity factor, the installed capacity scenario. The thing is, here it's telling me to upload a CSV file. Specify it directly in the application. Okay, you added a file upload for the installed capacity, but I'd like to be able to specify it right in the application itself. Also, what you could do here is at the same time enable a drag and drop file option. Good. Let's go here. Yes, we can also add it by year. Ideally, I could add more rows and the columns would be the years. When entering data in the table, the rows should represent the technologies, and for each column, we should be able to add a year. If we click to add a year column, looking good. Okay, this works. Let's go here now. Fantastic. Let's add the year 2040. If I put here that nuclear will be 3000 megawatts. In 2040 it'll be 0, and for solar it'll be 1000 as well. What's going to happen? Let's save the input. We have the scenario preview here. And here we have the results, which, well, okay. Although here it's not showing me the gas results. That's a big problem. It also puts several results on different parts of the application. No, let's see. But I think, let me see. You put several steps on different pages. I think it should all be simplified to fit on the same page. Everything organized by phases or sections where I can run each one and everything updates reactively. In theory, there was an option where I could have both agents work on the same application because I'm not fully trusting what codecs. I could work with Claude Code. I'm going to give it a vote of confidence. Thanks. All right, good. And now here it says optional, because in theory, it already has the demand data. It can also even work here with generation data. Let's see. And with that generation data, let's see. Thanks. Here what we can do is add more technologies, like gas, for example, and we run it, save the inputs, hit run, and here we have the results. But of course, the results show me a projection, but I want to see all the technologies, and I also want to see like a heat map with everything. Let me see. In the results, you must always show all the technologies, and if you need to modify the system to work that way, just do it. That's basic. Then for the result charts, I'd also like to add the aggregated year-by-year results for each technology in a heat map. Let's see, it broke something. Got an error. We need to rerun the application here. Save the input, run the simulation, good. The results should show all the technologies, good. Here I get the projection for each technology. I see something is failing here. Here the optimization is disabled. The optimization button is disabled. Why? From the results we have here in the simulation, it says gas. Right, since I didn't put anything here. Let me see. There's a problem here, and it's in the installed capacity. You need to include all the technologies, and the user will decide how to modify them. It must reflect the full table of all technologies for the years we already know from the files you have. Because otherwise it shows 0 installed capacity for gas, and then you can't run any simulation. And it says it will use this estimate as a baseline, but I'm not sure if, and I think so, because this is the file we had, the one we generated ourselves. And for nuclear, we have here at the end the year 2030, which, well, of course, since by 2027 they're already starting to shut down Almaraz. Nuclear should be here. Updated. Okay, now we're talking. This is something else. And here I click Save Inputs. I'll say here, let's see, we run the simulation, but the optimization still won't. And here I know we can see something, right? When nuclear, which is this one here, all right. Let's see how we could run the simulation. I still can't run the optimization. After running the simulation, the optimization is still disabled. So the system for the demand file could use the same thing we have, the same system that makes a future prediction. We could extend it all the way to 2050. Simulate. The demand is higher than the generation from the installed capacity. Okay. Well, we'll get there. We'll get there. Yeah, but by default, the configuration you should set is one that's feasible, so the user can run it without issues the first time. Thanks. Here you set those conditions. Gas technology. By default, it gives us something reasonable. All right. Thanks. Yeah, but that's impossible. I mean, I don't think demand would double. But it's really weird that no wind capacity shows up for 2027, no generation at all. Yeah, but it's very strange that there's no generation for 2027, wind generation, for example, or gas, and so on. Investigate further. Impossible. Now what's going up here is solar PV. But what's taking its place? There's nuclear, it's right here. But that seems way too low. I mean, it should be around 20%, at least in the early years. We have coal, which won't be around either. What it says here is 250 million. We'd be talking about the terawatt hours generated each year, if I'm not mistaken. Okay, so now it's creating a series of scripts to test that run that gives us something reasonable. And from there, it'll tell us. This is one of the advantages we have with artificial intelligence, and that is, if you know how to review how it works, how to navigate through the files, and then you apply your expert business knowledge, well, then the AI can't fool you, so to speak. Instead, I can you take control. Let's see here. Simulation results. Maybe this is more reasonable, but of course, generation isn't going to increase that much. Then over here, the technology breakdown. Let's see, demand increases way too much by 2030. I don't think that's right. It'll grow, but at a very slow pace, and I don't think it keeps growing forever. I mean, at some point, it'll flatten out. And then regarding I'd like to see some kind of progression, also in terms of studies, like comparing CO2 emissions by technology, or maybe having a panel where I can choose the technologies and compare them side by side. I don't know. Something more interactive to explore different scenarios comparing technologies as well. But anyway, we'll start going in circles here. So what we're going to do is we'll wrap it up for today. I'll probably continue with the second part of this stream to do a proper simulation and end up with a good application that you can actually use with a solid system for applying the constraints, and I'll publish it. I'll also show you how to use it. For next time, I will use Cloud Code. I'm more comfortable with it. I have more tools installed here. The codex, well, it's fine, but I don't know. I think in some ways it leaves something to be desired. Something to be desired. So anyway, guys, it's been a real pleasure on my end. I appreciate those of you who followed along this far in the live stream. For those who couldn't, you can watch the recording. It'll be available on YouTube. Most importantly, the logic I explained at the beginning about how the machine learning models make the estimates and how to have that evaluation between training and development. If you want to learn more about what we work on, you can visit us at datons.com. We offer services in both English and Spanish. All of these solutions and any others that you might need with applied programming for data. You'll see here case studies that we've already worked on with other clients. You can also check out here the blog where you'll find tutorials with code about, for example, business opportunities in arbitrage, in electricity markets. Now with the battery topic, which is quite interesting, and if you think that we could collaborate on some project or get to know each other and see how it goes, well, you come here, schedule a call with me. We get to know each other, see how it goes, get on the same page, and if down the road an opportunity comes up to collaborate on a project, well, we'd be delighted to contribute our little grain of sand automating processes with artificial intelligence. See you next week. But first, let me tell you that you can try. The tool, the application that searches for you in the BOE. Here you can see that there's access to the vast majority of laws collected. You can see here, for example, several case studies. If you click, you can even see the versions that exist. And it does the diff view of specifically what has been modified, and not only that, but this technology. You can also integrate it into your trusted chat, ChatGPT or Claude AI to access legislative information and make queries about the latest updates. Here we have all the laws that we've ingested. For example, if we type here electricity, you'll see here, for example, the electricity sector law. On top of that, you can search with a built-in search engine for what you specifically need. For example, energy storage. We search here the results and it shows us specifically the articles where we need to look at the information and also how it compares over time. And since it was first conceived in 2013 until today. So anyway, if you want to get access and so on through the chat, you can sign up and try the tool. On my end, thank you so much for following along all the way here, and see you next week. Cheers. And